Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff. This is part of the awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Van Dixon with us today. Hello, Van.
Hello. It's lovely to be here.
Well, I'm happy that you're going to talk about this very lovely article we're going to get to. And Van, what's your geolocation? Where are you at?
I'm in Baltimore, Maryland.
Baltimore.
Uh, yeah, it's the middle of March, and we've just had a week of like 70-degree temperatures.
There's no snow.
No snow. Um,
70. Wow.
Yeah, all the flowers are out. Baltimore is spectacularly beautiful in the springtime,
Lovely.
but this week it's cool again, back in the 50s. So I'm hoping that all the flowers will stick around for a few weeks now. Yeah.
Cross fingers, cross fingers.
Yeah.
So I'm in Phoenix, and we are definitely in our spring. We're getting sort of the battle between the rain and the sun, and today will probably be about 75 or something like that. So it'll be quite pleasant this afternoon. But very cool, very cool. And Van, what do you like to do for research?
So I'm mostly a UV spectroscopist,
Mm.
and lately, well, for a long time, I've been studying hot stars in globular clusters,
Cool.
Which turn out often to be sort of post-AGB stars that have evolved up the AGB and moving on their way to becoming white dwarfs, but not always, as we shall see.
Shall see. There are other ways to make them UV hot.
Yep.
Very cool. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Observations of the ultra-bright star ZNG1 in globular cluster M5 in GC 5904. And Van, take us away.
Okay. Zinn, Newell, and Gibson in 1972 published a catalog of what they called UV bright stars in globular clusters.
Mm-hmm.
These are stars that are hotter than that is, brighter than the horizontal branch and bluer than the red giant branch. And there are a handful of them in every cluster. Most of these stars are stars that have evolved up the AGB, the asymptotic giant branch.
Yes.
And have lost whatever outer envelope they're going to lose and are on their way to becoming white dwarf stars. So they would be the central stars of planetary nebulae, except that the globular clusters don't have planetary nebulae. They're like 4 of them in the galaxy in globular clusters, right? So most of these stars, the masses are too low to make it to the tip of the AGB, and so they peter out and leave early. And so they're less luminous than you would imagine stars to be if they were central stars of planetary nebulae. So anyway, for the cluster M5, they give a list of like 6 or 7 of these UV bright stars. And the brightest of them is ZNG1. Every cluster, they started over with 1, so every cluster has a ZNG1. So this is the one for M5. Okay, so the star was sort of discovered again in 1983 when Ralph Bullen and his colleagues imaged the cluster in the ultraviolet with a rocket-borne telescope. And they found this one hot star about 20 arc seconds from the cluster center. They followed up with IUE spectra, and it showed that this spectrum had strong carbon-4 and nitrogen-4 lines, and carbon-4 and nitrogen-5, 1550 and 1240. There's also this funny emission feature at nitrogen-4, a semi-forbidden line, 1487. All right. So the authors suggested that perhaps that emission feature was evidence of a planetary nebula.
Ooh.
Later on, Klaus de Beer took a whole bunch of IUE spectra, added them together, and fit them with Caru's models.
Okay.
And he got a temperature of about 28,000 degrees and
Hmm.
argued that the nitrogen line only appeared in one of the IUE spectra. So he argued that that was not real,
Huh.
was an artifact.
Okay.
So Napoletsky and Hebert in '97 looked at the cluster with the Hubble Space Telescope.
Okay.
They got H alpha imaging with PIC2 and spectra with GHRS,
Cool.
and they found that there was no evidence of a planetary nebula around this guy.
Okay.
And then the star has these really strong lines, again, from carbon and nitrogen and a bunch of other photospheric features.
Hmm.
They estimated a temperature much hotter, about 40,000 degrees.
Ooh. Okay.
So when I was 20 years ago, 25 years ago, we looked at it with views to try and learn more about the star.
Cool.
And so we had data from cycle one, a few thousand seconds, and we were able to estimate a temperature of about 44,000 degrees, log G of 4.3, and a rotational velocity. At that time, we got a value of 170 kilometers per second. So this is where I'd like to show a figure from that 2004 paper.
Sure.
Okay.
Let's go ahead and get out of here and let you do a figure share from 2004.
Okay. So a little blast from the past here.
All good.
Can you see that?
I do now. I see figure one.
All right. So this is figure one from the 2004 paper. You can see it's pretty noisy. That's okay. So I'm looking at this carbon-3. It's an excited state line at about 1175 angstroms. For these really old stars, you should expect a rotational velocity of basically 0. And this gray model is a model with a rotational velocity of 10 kilometers per second.
Okay.
And the other models are 100, 200, and 300 kilometers per second. So
Gotcha.
it's clear just from this figure that the rotational velocity is pretty high, somewhere around 200 kilometers per second.
Cool.
So, all right, I will stop sharing.
Good. Okay. Well, thanks. That was a value add, people.
Yeah, you like that?
I like that. That was good. Let's go back.
So, oh yeah, go back to the real paper.
Oh, well, they're both real. It's just this one's newer.
Okay. So,
Okay.
so we, my colleagues and I, got more data with Fuse later on. So we end up with much better spectra. And a few years later, William Zech and Chris Hauck and his colleagues observed the star with STIS on HST.
Okay.
We got high resolution spectra from that. And what I didn't mention was that the Fuse spectrum showed a interstellar medium absorption at high velocity. Two lines, one about 150 kilometers per second, blue shifted towards us, and one about 100 kilometers per second, blue shifted, towards us.
Yep.
And either this is like material being blown off of the star, or it's some cloud along the line of sight between us and because this globular cluster is pretty far off. Right. And so they investigated this and decided that in fact it is not circumstellar gas. It's a high velocity cloud falling in on the galactic, toward the galactic plane. So that was interesting. Yeah, and but the point is that we now have STIS data of the star as well. So in this paper, we take the Fuse data from Fuse cycle 1, the Fuse data from Fuse cycle 4, and the STIS data, and try and understand the star using these higher signal to noise data.
Cool.
All right.
Cool.
So, um, so uh, the next section is about the data itself, the observations. We can just skip, I think, let's try table 1. Yeah.
Mhm. Yeah.
So the first data were taken 3,700 seconds, cycle 1,
Yeah.
another 27,000 seconds with cycle 4, which really helped a lot.
Absolutely.
To noise. And
Yeah.
then the two observations with STIS were that same year, 2003.
Good year, 2003.
And STIS has it's much higher resolution than FUSE costs. And
Yeah.
that comes in really handy for the interstellar medium work when your star is spinning at 150 kilometers per second.
Indeed.
High spectral resolution is less helpful.
Mm-hmm.
But anyway, we're glad to have it. So I will skip to the analysis section, I think,
Okay.
section 3. So the FUSE data are punctuated by lots of ISM lines, mostly molecular hydrogen, which goes all the way to the Lyman limit.
Okay.
And the STIS data are mostly exploring higher ionization states of interstellar lines. So here is where I mentioned the intermediate, the high velocity cloud that's falling in on top.
Mm-hmm.
They estimate velocities of 135 kilometers per second towards us, and then minus 18.
Okay.
Oh, for the atomic hydrogen. Anyway, we used the models of the ISM models of Zech et al. To model the ISM lines in the spectrum, and the ones that they didn't model, I just modeled by eye because that's good enough for what I wanted
What we need to do here. Yeah. Okay.
All right. So let's go on to the model atmospheres. I'm using T-Lusty models by Yvonne Hubany. So it's non-LTE. And we learned before in 2004 that the CNO abundance, the star basically has no hydrogen, very little. It's mostly a helium star.
Yes.
And the CNO abundances are very high. So the models have hydrogen, helium, and CNO, and mostly, I don't know where I say this, but oh yeah, there it is. Because the star has so little hydrogen, usually when you're doing a stellar model, you quote all of the stellar abundances relative to hydrogen. If you don't
Yes.
have any hydrogen, that's not so helpful. So the Hubany and Lenz recommend using helium as the reference spectrum, the reference element. And it's easy to do. You just change. It's an easy thing to change. So all of these models use helium as the reference,
Okay.
and then we actually compute the hydrogen to helium ratio later on. So all of these things are relative to helium. So that's the point.
Cool. I'm with you.
And we use SynSpec, which is their model, their routine to turn model atmospheres into synthetic spectra.
Cool.
And, in all the usual ways. I don't try to normalize the data. Instead, I try and include an interstellar absorption curve, the Fitzpatrick extinction curve. I use the ISM model that I discussed above from the Zech paper, and that gets me, and I know the distance to the cluster, so that allows me to scale the model, and then I cheat a little bit and fine tune it to match the data in some continuum region nearby. So that's how we do the scaling.
Fair enough. Fair enough.
The thing to keep in mind is that because the star is rotating so quickly, all of the absorption lines are very broad and very shallow, and could be, or probably are blended with something else. So that makes
Okay.
that complicates things in a couple of ways. It's very hard to define the continuum when lines that would normally be very narrow are all very broad. And
Yeah.
so there's probably no piece of real estate that's really a continuum. So one of the ways that I deal with that is just to assume that I'm getting it wrong by about 3%. So
Okay.
you see down there, I fit everything twice, once with my best guess at the continuum,
Yes.
and then once I just scale the model by 0.97.
I'm with you.
And do it again,
Well,
and I add I figure out the difference in the abundance that you get for whatever feature you're looking at, and add that into the statistical errors.
Okay.
So that's and in some places we'll see later on the abundances that we get have really big error bars, and most of that is coming from that 3% uncertainty in the continuum.
Gotcha. Okay. I'm with
The
you.
statistical errors are always very small.
I'm with you.
Okay, so let's move on. So I've already shown you the figure from 2004 about the radial, how I estimate the radial velocities from the carbon-3 line.
Yes.
And I can also use that feature to estimate the radial velocity of the star. And so that gives me a value of about 100 and let's see. Yeah, okay. So this paragraph is saying that we do this twice. That feature appears both in the fused spectrum and in the STIS spectrum. Yes. So I fit it twice, I get two numbers and I combine them. And so the weighted mean of the two values is a heliocentric velocity of 43 kilometers per second and a rotational velocity of 157 kilometers per second.
Okay, cool.
The cluster has a mean velocity of about 53 kilometers per second. So we're within 2 sigma of the cluster mean.
Yes.
So that's good. That suggests that the star is in the cluster.
Yes.
Which is helpful because that's going to be a big part of our assumption moving forward. One thing to think about is this next paragraph. There's another star that was observed with fuse about the same time, and that was originally the original observers, the people who analyzed the spectrum, Lance et al., computed a rotational velocity of 100 kilometers per second from this helium-rich BE star with a phone number PG 1544 plus 488. But later on, optical observers using high-resolution spectrograph determined that the star is actually a spectroscopic binary. So it's not really rotating that fast.
Okay, gotcha.
And they were able to they went back, got the fuse data, chopped it up in little pieces, and computed the velocity for each piece. And showed that the radial velocity was changing with time. Yes. So I did the same experiment just to see. Yes. So that's figure 1 at the top of the page.
Okay, let's take a look at figure 1 here.
Yeah.
We got a binary here.
Yeah, good. So so I cut the data, the fuse data. So this is the cycle 4 fuse data where it was actually observed for several hours over the course of 3 days. Cut it up into 1,000-second chunks.
Yes.
And computed the radial velocity, measured the radial velocity for each chunk.
Okay.
I found, and so the 3 different subplots are from 3 different days worth of data. And so the first day, it's basically consistent with being a flat, the radial velocity is constant within the error bars. That's gratifying. On the 3rd day, it's also pretty consistent with being flat. On day 2, yeah,
sort of.
Day 2 is less consistent with being flat, but there's no pattern.
Fair enough.
So,
fair enough.
Yeah. So my conclusion is that there's no data, these data do not support the hypothesis that the star is a binary.
Right.
And maybe they suggest that my error bars are too small. I don't know. Anyway.
We'll come back to that. We'll come back to this. Okay.
Yeah.
Yeah.
I think error bars are always too small. Anyway, I looked to see if it was a binary, and I am not able to argue that it is. So we're going to proceed under the assumption that it is not.
Okay. We'll come back to that. Yep. Cool.
So what happens next?
What happens next is we get our effective temperatures and abundance.
Oh, yeah. So that takes us to figure 2.
Mm-hmm.
So a couple of different ways you could try and do the effective temperature. A really nice one is to compare different ionization states in the same element and see at what abundance and temperature they give you the same answer. So really quickly, if you haven't thought about this for a while, let's look at the nitrogen in the middle there. The solid lines are all nitrogen 3 features from the fuse spectrum. Actually, all this data is from fuse. And you see, so what I do, the leftmost point represents a temperature of 41,000 degrees.
Yes.
So I have a series of models with this temperature and various nitrogen abundances. And I fit each of these lines, and I derive the nitrogen abundance, assuming that temperature. So that's plotted here with error bars.
Mm-hmm.
Then I do the same thing at 42,000 degrees and get the abundance for each of those.
Okay.
And for 43, 44, 45,000 degrees. So that's those solid curves plotted. And the curves are not a straight line. I actually fit a low order polynomial to them.
Okay.
Right. Then the dashed line is a nitrogen 4 feature. Let me come back and say what this curve tells us. Remember, so at 41,000 degrees, there's lots of nitrogen 3 in the atmosphere. And so you can fit the lines with a relatively low nitrogen abundance. Okay. But as you raise the temperature, more and more that nitrogen 3 is ionized to nitrogen 4. And so you need more and more nitrogen to reproduce the absorption lines. And that's why the derived abundance rises with temperature.
Cool.
Okay, so the idea is to do this for different species and find out where they cross. So I have one nitrogen 4 line, 955 in the fuse spectrum, and it has the remarkable property that it seems to be basically immune to temperature in this region. So now you look and you see where they cross, and they cross between 43 and 44 thousand Kelvin. I suppose one should quit while one is ahead.
Always.
I have more lines, and I went to look. So if we scoot up to the top of the figure,
okay,
carbon, you'll see the same thing. Here I've only got different carbon lines. The two on top, the green and red ones, sorry for my colorblind colleagues, represent that carbon 3 line that we were looking at earlier at 1175. That's carbon 3, the excited state of carbon.
On the figure 1 that we looked at in the 2004.
Exactly.
Okay, I'm with you.
The other curves, a little lower down, are other carbon 3 lines elsewhere in the spectrum. And you see that they cross at a cooler temperature, like maybe between 41 and 42,000 degrees.
142, yes.
Down there. So the good news is that we're all in the low 40s. The bad news is that they are a little different.
Right.
And we can go down and look at the oxygen lines now.
Let's do oxygen. Let's get a third one. Third vote. Yeah. Okay.
Well, the third doesn't even bother to vote. The oxygen lines, I have oxygen 3 and oxygen 4 lines, and they remain stubbornly separate across this whole region.
Yes.
But notice the ginormous error bars on all of these things.
Yes.
Again, they're really, really broad, very shallow, and it's hard.
Yeah.
It's just hard.
Wow.
Yeah.
Okay.
So two more things I want to say. The first one is I measured like twice as there are 20 lines on this figure. I measured another 20. And when I first plotted them all up, it just looked like a bowl of spaghetti.
Right.
And after much thought, I decided to toss the ones that either had error bars so big that they didn't constrain anything,
Okay.
and also the ones that gave results that were completely nuts, like, super solar or whatever abundances.
Yeah.
And just assume that they're blends with other things. Yeah, so this is the best that I could do, given these data.
Cool.
And then the other thing to say is how you get an actual number out of that. So
Fair.
if you look on the right hand side, you'll see that I have two equations in this paper. That's one of them, which looks familiarly like the definition of chi-squared.
Mm-hmm.
Right. So I wanted to come up with some numerical way of getting an answer by combining these data. So I at each point I compute a value of chi-squared. So the y sub I is would normally be a model, and instead it's just the weighted mean of all of the data for each element. And the y of x is the measured value for each element.
Okay.
Right?
Okay.
And then sigma is the uncertainty that I've computed. And I actually did this. Not every 1,000 degrees, but I went in and used, because I had fit curves to all of these. I calculated this number for every 10 degrees all the way across.
Okay.
So I would have slightly more resolution in the temperature.
Right.
And so I minimized that. And so that means that the oxygen lines with their huge error bars don't contribute very much to this whole discussion.
Yes.
And it's mainly the nitrogen and carbon lines fighting it out.
Yes.
So the answer best fit comes out to be about 43,000 degrees.
Okay.
And I looked at delta chi-squared to try and get limits. Yeah.
Sure.
So the upper limit to the temperature is 44,400 Kelvin, which is where the point at which chi-squared rises by 4.72, which is the formal value if there are 4 interesting parameters that you're trying to fit. So that's 3 temperatures, three abundances, and a temperature.
Cool. Okay.
That's true if if it's Gaussian distributed and all that stuff, which is certainly not the case. But this is, again, the best you can do, and it gives a reasonable value. So that's how we get temperature for these things, and the CNO abundances, which are up there in that table up above.
Mm-hmm.
Yes.
Okay.
Okay. So let's move on and get the helium abundance and surface gravity.
That's our normal.
Yes.
Hydrogen.
Yeah. Okay. So surface gravity we get from fitting the helium line, which is the next figure. Yeah, there are 2 helium lines in the spectrum, one in the fuse. Well, actually, there are a bunch, but these are the 2 that are least contaminated by other things. So the 958 line is in the fuse spectrum. You see those narrow absorption features. Those are interstellar lines, mostly molecular hydrogen. And the one at 1640 is the strong helium line in this spectrum. And you can see, again, there's probably another stellar feature on the blue wing, and then maybe a ISM line on the red wing.
Yes. And what are these blue horizontal bars up here?
So that's the parts of the spectrum that I actually included in the fit. So I'm avoiding those interstellar lines.
Yeah.
Yeah.
Right.
Because the lines are so broad,
Mhm.
but there's still, you can cut out the ISM lines and there's still plenty.
There's still
to
plenty
look
of
at.
signal there. Uh-huh.
And those things are set by my program, and the program is looking at the model of the ISM. So it even knows about things that are not obvious to the eye.
Okay.
Right. So anyway, you can see that the helium lines are relatively sensitive to the surface gravity. Those models have gravities of 4.3, 4.5, 4.7.
Log G.
And
Okay.
and I use that to get I get two different I fit them separately. I get two different values. I combine the two, and it gives me my value, which I think is like 4.47 or something, just a little less than 4.5.
Fair enough. Okay. Okay.
I think, yeah.
We're good.
So let's go on. That gives you the surface gravity. Let's go on and look at the hydrogen abundance.
Okay.
Normally, the next figure, normally you would be calculating the helium abundance, but in this cluster. So because the star is so hot, every hydrogen Balmer line is paired with a helium line, ionized helium line,
Cool.
at about the same wavelength. So you can see here are four of them from the fuse data, and they're right next to each other. So and then on top of all of that are the atomic interstellar hydrogen absorption. So these flat bottom lines are hydrogen absorption.
Yes.
And then the molecular hydrogen features on top of that. So there's actually very little real estate to use to determine this. But the good news is that the star has a positive velocity of, what did we decide, like 40 kilometers per second or something. And the ISM has a negative velocity. So they end up being about 50 kilometers per second shifted, the ISM lines. So basically what we're looking at is the red shoulder of this stellar feature, and to try and see how much hydrogen is left. And I forget the scaling. That is, there are four models there.
Gotcha.
Yeah. And I can tell you here,
Okay.
the green line is has lots of hydrogen. That's basically 5% hydrogen. The orange line is 1% hydrogen, and the blue line is 1/10% hydrogen. And you can see that even it's pretty obvious that the green line, the 5% hydrogen line, dramatically over predicts the absorption that you'd see. Again, those horizontal blue lines represent the part of the spectrum that actually gets included in the fit, which is pretty small.
Yes.
But just from the figure, it's obvious, I think, that there is very little hydrogen in this star.
Yes.
And I think the number we end up with is about the hydrogen to helium ratio is about 0.02.
Right.
And
minus 1.7, minus 2. Yep. I'm with you.
Okay. So there's a little bit of iteration that goes, because once we've tinkered with the hydrogen to helium ratio, you need to go back and make sure that the gravity is okay. And I do all of that, but the numbers don't change significantly.
Right.
So that gives us the values. Okay.
Do we have a converged solution, so to speak?
Yeah. Okay.
And finally, we get stellar parameters. I think we ought to talk about.
Yes, you get this. All right. So 43,000 degrees, log
Uh-huh.
G of 4.47. We'll get to the other numbers later.
Okay.
But I'll just say that both the
Okay.
stellar radius and mass are 0.9 times that of the sun, which already tells you that this is not a object on its way to becoming a white dwarf. This is something else.
Indeed. Okay.
Okay.
Yeah.
So real quick,
Yeah.
the next thing in the paper is to get the metal abundances for the other elements.
All right.
And I'll just tell you, yeah, there they are. So these are the lines that are available. There are two silicon lines. Again, I had to use just one wing of them
Yeah.
because the other side there's interstellar absorption.
Mm-hmm.
There's one sulfur line available. Um,
Nice.
and then for the iron lines, there are no strong iron lines, but there's this region between 1370 and 1380 where there's lots of weak iron lines and not much else.
Yes.
So I fit that whole region to estimate the iron abundance.
Yes.
And you can see from the 1, 2, 3, 4, 5 column 5, the sulfur and iron lines that have really big error bars, and that's all coming from the multiplying the model by 0.97.
Ah, that's your okay. 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 Mm-hmm.
Particularly the iron, that makes sense because we're really just fitting the level of
Yeah, the general. Mm-hmm.
sort of pseudo continuum.
Mm-hmm.
Um, but that's what you can do.
Gotcha. Okay.
All right. So the next section is about the stellar wind in the paper, and I propose that we just so that's going to be, if you're looking at page 8,
Mm-hmm.
figures at the top of page 8.
Let's go to page 8. Page 8. There we go.
Okay, so I won't belabor this, but the thing that struck me about the data right away, and also previous observers all the way back to IUE, was these huge absorption lines, which are they're all wind features. Okay, so in the figure, we got these three strong lines, oxygen 6, nitrogen 5, carbon 4. They're resonance transitions, right? And they're doublets. So the horizontal line
Okay.
is indicating the position of the two components of the doublet.
Okay.
So the the thing to notice is that you can't really see them
Not really.
because well, for oxygen they're just not there. There's not any oxygen 6.
Yeah, we saw that before. It was just flat.
Yeah.
Mm-hmm.
So yeah, it would have been flat otherwise. There probably is a little bit of nitrogen 5 and some carbon 4, but they're all smeared out. So that's that. And then the broad P Cygni profiles are, I guess it's most obvious in the oxygen line on top, right? You can see the absorption on the blue side and the emission on the red side,
Okay.
within a few hundred kilometers per second of 0.
Mm-hmm. Mm-hmm.
The blue vertical lines, so the thing to notice are these discrete absorption components, which are these huge narrow troughs, I don't know, 500 kilometers across,
Yikes.
across, in both components. So there's one for the O6 line. They're all lined up.
Ah,
Yes.
it's that. Okay.
Yes, that's the point. Is that the discrete absorption components, or DACs, line up at about 1,000 kilometers per second, minus 1,000.
Gotcha.
Yes, and so I've arranged the diagram so that for the blue component of each species, they all line up. So that's telling you that. The red component gets its own blue line, and they're all different because the difference between 1548 and 1550 is different than between 1032 and 1038.
Gotcha. Okay.
Right. But the point is that there are strong PCMU profiles and strong discrete absorption components in both of these, in all three species.
Lovely.
And then if you look particularly in the nitrogen 5 and carbon 4 lines, the wind feature continues down almost to like minus 1,500 kilometers per second.
Mm-hmm.
Yeah. So the wind continues out for a long ways.
Wow.
So
Okay.
really, this is just a phenomenological plot.
Agreed. Yeah.
One thing in my reading, I've learned that the presence of these things is related to the rotational velocity of the star in other stars, and so the fact that this star is rotating with such a high velocity, maybe it's not a surprise that it's got these discrete absorption components.
Okay.
And another thing that's really interesting is that the fuse data, the two fuse observations were made like in 2000 and 2003, so 3 years apart, and the DACs line up perfectly.
Lovely. Cool.
They should move with velocity and eventually sort of blow away. And maybe they do, and I just got lucky. But I don't know.
TBD.
TBD, yeah. That's an exercise for the reader.
Classic. Very good.
We can slide down to the bottom of this page and
Sure.
look at the next figure.
Ooh, okay.
Just very quickly.
05.
Yeah, so Dirk Massa has studied these stars a lot, and he has a little IDL program that you can use to fit these lines. And so I played with that. And the dotted and dashed lines are the transmitted component of the light, so from the star that goes through, and then the scattered component is the green part.
Mm-hmm.
And the way it works is what you play with is the opacity tau as a function of velocity through the wind, and you just try the numbers until you can reproduce the shape.
Okay.
And so that's what I've done. And so the dark blue line is my photosphere stellar spectral model times his model for the wind feature, right? And it does a reasonable job reproducing that thing. And so you can calculate m dot, the mass loss through the wind, and play with other games. But I propose that we not do that and just go on.
I agree with that proposal.
Yeah. So so the whole point of this paper is to explore the possibility or try and figure out what this weird star, how it got to be so strange. So now let's start doing that part of it.
Okay.
So the next page, the next figure 7, shows the just the abundances that we've calculated for this guy. Remember, the stellar abundances are all done relative to helium, and anything in the literature is quoted relative to hydrogen.
Yes.
So my solution, just so you could compare them, is I assume that iron is neither created nor destroyed in this star, and so I applied everything relative to iron. So the big black stars are Z and G1. The horizontal lines are the sun, just for fun, and the M5, the orange red lines represent published values for the rest of the cluster.
Okay.
So these are going to be giant stars in the cluster.
So
the thing just to notice is that the CNO abundances are all very high and sort of about the same. There are error bars on the carbon and nitrogen lines, but they're pretty small in this plot.
Yes.
The oxygen lines, remember, those were all over the map.
Right.
So that's what's, but it's they're all pretty high. Silicon maybe have the cluster value. And I don't know what the cluster value is for sulfur, but it seems to be at least less than solar.
They're about roughly solar for silicon. Sulfur.
Yeah.
Sulfur is way down. Yeah, yeah.
Sulfur's
Okay.
way down. Yeah. So
Wow. Okay.
yeah, what do you do to this? Um,
Hi.
so
Merger.
yeah, merger. So um, I've thought over the years about various explanations for this.
Yeah.
I was talking with a colleague about a year ago, and he as soon as I explained what the star looked like, he goes, "Oh, it must be a merger remnant of two helium white dwarfs." So and I thought, okay, so I started reading about them, and yeah, Marcello Miller Bertolami.
Which we have done a video with one of his articles. People go check it out.
Okay, he's a lovely guy.
He is.
Uh, and so I started reading, and while you're there,
Oh, okay. Sorry.
Simon Jeffrey has studied these and modeled these stars for the last 20 or 30 years,
Mhm.
and was very helpful and kind when I was asking him, pestering him with questions about all these things.
Good shout outs. Good shout outs.
Yeah.
Very good.
Now that being able to talk to people, I don't know, that's one of the fun things about this job, and sharing ideas and getting excited about each other's work.
Indeed. Indeed.
Okay, so if you were to plot these things on various people, including Marcello, have calculated evolutionary tracks for stars, post-AGB stars, right?
Yes.
And if you look at his tracks, you'll see that this star falls just where you would expect for an object that had evolved off the blue horizontal branch and had gone up partway up the AGB and across. But that's not what's happening.
Yeah.
The enhanced CNO abundances, the absence of hydrogen in the atmosphere, and the high rotational velocity are not consistent with that scenario.
Yes.
So yes. So we're going to look at Marcello's suggestion of a helium white dwarf merger.
Okay.
So let me just remind you real quick how this works. In order to get a helium white dwarf, you already have to have a special situation. You have to have a binary system. So the first star heads up the red giant branch, and as it expands, it overflows its Roche lobe, and the whole envelope falls onto the lower mass star. And you end up with an object that's basically going to be a white dwarf, but it's got a helium core instead of a CNO core, like objects that evolve normally. Right? Because the stars that are going up the red giant branch, the whole point is that they've run out of hydrogen in the interior and they're just got a helium core.
Yes.
All right. So that,
there you go.
Yes, that goes on for a while. And then eventually the lower mass star, which is probably now the higher mass star, becomes a red giant. It expands and it loses its material, probably the white dwarf, or leaves the system or whatever. And you end up with two helium white dwarfs in a binary system. And then you wait like the age of the universe, and eventually the two stars merge. They radiate away their gravitational energy through gravitational radiation, and they merge. And this sounds like this would never happen, but we know that most of the stars in the galaxy are binary, and it seems to be a very common phenomenon. So in this figure right here, all those little red dots are known helium subdwarf O and B stars, and all of those are assumed to be the progeny of these helium mergers, white dwarf mergers.
Very cool.
Okay, so Simon Jeffrey and various students and colleagues have calculated models of how these things would evolve. And so when they do merge, they end up sort of swelling up into be like a red giant, a new red giant,
Right.
powered by a helium burning shell, because there's
That
plenty
makes
of helium, right, in these stars. And then eventually they, collapse and heat up, and eventually fall onto land on the helium burning main sequence. So these two tracks, right, in this figure, the orange and blue ones, are for 0.8 and 0.9 solar mass merger remnants
Okay.
that are collapsing, heating up, and moving down to the helium main sequence. So the black star represents ZNG1.
Right.
It is presumably on its way down. It would be super cool if it had landed directly on the blue curve.
Yeah, it would have been very cool.
But
uncertainties persist.
Yes, uncertainties persist. Where this is all, if this were all, if we had all figured out, we wouldn't be doing science.
We wouldn't be doing this.
So anyway,
mysteries are good.
That's one piece of evidence that this would be realistic. The next one is in figure 8 on the next page, which
figure 9, and here we go, and we get the distribution.
9, yes. Right. So let me tell you what this plot is, and then we can talk about what it means.
Okay.
So these are this plot has shown up in a couple of different papers before, and I'm reproducing it here. It's like 35 or 40. Again, helium O and B type stars. And what we're plotting on the y-axis is the logarithmic mass fraction of helium, nitrogen, and carbon. And the black points are carbon, and the stars are arranged in order of increasing carbon abundance.
Yes.
So you see there are sort of two populations. On the left-hand side are these low carbon stars. And then there's a sort of a jump. And then on the right-hand side are all these high carbon-rich objects. The horizontal black line represents the solar value for the carbon mass fraction. So you see that these guys, the carbon-rich guys, are super solar. They're carbon abundant. All right.
Interesting.
The green points are nitrogen, the nitrogen abundance. And we see that on the left-hand side of the figure, all of the carbon poor stars are nitrogen rich.
Yes.
And the green horizontal line is the solar value. So they're, half a dex, almost a deck.
Yeah.
More nitrogen rich than the sun.
Yes.
On the right-hand side of the figure, the carbon rich stars are nitrogen poor, but the nitrogen values are scattered all over the place.
Fair enough.
Okay. And then just at the top, for completeness, those are the helium abundances. And you see, compared to the sun, they're all, they're helium stars. There's no hydrogen left in the sun. Okay. So in the very, very middle, just by chance, our ZNG1 lands. That's the star.
Here we go.
Yes. So we see that it is carbon poor and nitrogen poor relative to all these other guys. So it's carbon poor like the carbon poor stars, but unlike them, it is also nitrogen poor.
Yes.
Relative to the sun.
Yes. That's interesting.
Yes. Which either means that it's some kind of magic transition object because it's falling right in the middle, or I don't know, maybe it means something else. But I was actually thought that this, again, you could wish for a better fit, but I'm happy that it behaves as well as it does compared to these other guys. So a couple other things to say. So another paper by Simon Jeffrey and another of his collaborators models these trends with various evolutionary scenarios for these stars. And they are able to reproduce these ratios by assuming that the merger remnant has different masses from like 0.5 to 1 solar mass. And different values yield different ratios of all these things. And our star, as you might imagine, falls right in the middle. And it's consistent with a mass of about 0.6 and change solar masses.
Well, that's an interesting number.
Which is, more than the white dwarf, than an ordinary white dwarf, a little less than the value that we calculate. But again, everything's got big error bars.
Beautiful.
But it was satisfying to see that they can reproduce it at all.
Exactly.
With their models. Right.
Cool.
And then the one last question is, how do you get the star? Why is the star spinning so fast? The other stars in that last figure that you're about to scoot away from, they all have velocities, as I recall, less than 35 kilometers per second, rotational velocities. So they're pretty low. Our star is moving very fast.
Right.
Another of Simon Jeffrey's papers explores how you lose the angular momentum from this rotation.
Correct.
And the idea is that what they did was they calculated models assuming no loss of angular momentum, and just to see what happens.
Sure.
And so again, the two stars merge, you get something that looks like a red giant. As time goes on, it collapses and heats up, but it spins faster and faster and faster. And if you didn't have any mechanism for ejecting
momentum transport,
it would end up spinning at 1,000 kilometers per second.
Right.
And that's not. In fact, all these guys are about 35 kilometers per second or less. So there's got to be angular momentum loss, probably by mass ejection, probably when the stars are merging.
Okay.
So why all these other guys managed to get down to 35 kilometers per second and ZNG1 is still at 150 is another open question. But it is telling you something about probably mass loss when the stars were merging.
Okay. Cool. Very nice.
So this is basically it. This is what I managed to learn about this very funky star.
It's official IAU name now.
Yeah.
Very funky star.
But it's cool, and
cool.
And it's there are so few of these objects in globular clusters in particular. That is UV bright stars. It's turning out that each one of them is like unique and strange in its own way, and this one is maybe the strangest of all.
Awesome, very cool. Dan, I want to thank you so much for walking us through your very beautiful AJ article. Thank you.
You're welcome. Thanks for having me.
Yeah. And you touched on it a little bit there at several points. So let me just go ahead and push on it a little bit and ask, where do you think we go from here given the published article? For example, one of the uncertainties was whether this is a binary object or not. So is there additional observations coming that might be able to tell whether we're binary or not a binary, and so on? Are there other plans to do observations of this object, and so on? So just sort of where do we go from here given the published article?
Sure. So one thing that Napolotsky and Hebert point out in their paper was you can't look at this guy from the ground because there is a companion nearby, a G-type star about half an arc second away. Okay. They argue that the two stars are not gravitationally bound, that they're just a line of sight projection, which is not uncommon in a globular cluster.
Sure.
But it is quite possible. I mean, it could be that there is another companion that is not seen, especially if it's hot and you wouldn't see it from the ground. So you could go back and look at the star and try and determine if it's, you know, a binary companion. My actual current thought is to take a break from the star itself and think more about that high velocity gas along the line of sight.
Okay.
Chris Houck and his student
Yeah.
argued that this is not associated with the star, but is in fact a high velocity cloud falling into the galactic plane. But if it is, it's got carbon, nitrogen, and oxygen metallicity that's higher than any other high velocity cloud that's ever been seen in the whole entire sky. So, you know, is it really?
Yeah. Really?
And fortunately, it's sitting in front of a globular cluster. So there are lots and lots of stars that you could use to probe the line of sight through the star, including like
Yes.
blue horizontal branch stars
That would be
that
cool.
have enough flux in the UV that you could actually go back and see all these guys.
Cool.
So I'm thinking about so now you know my secret plan for a Hubble proposal is to go and look at you know, maybe half a dozen of these stars and see if you can map out the extent of this cloud and either learn more about it or figure out whether it really is associated with the star or is really telling you something new about high velocity clouds falling in on the galaxy.
Beautiful. Awesome. Oh, well, I really look forward to seeing this mystery get some additional light, so to speak, over the next couple of years. It'll be very cool. Very nice.
Thanks.
All righty, and that will do, everyone. And I hope this made your ultraviolet astronomy day just a little bit better. And we will see you on the next one. Bye-bye.